In this last part of video 2, we're going to talk about the hydrophobic effect. So, water is, of course, the solvent that all macromolecules that we care about live in, and it turns out to be a very unusual liquid. So, just to remind you, water, of course, has two protons that can form hydrogen bonds, act as donors, two lone pairs that can act, lone pair of electrons that act as acceptors, and these potentially can form up to 4 hydrogen bonds. In fact, in liquid, in solid ice, you do see these networks of hydrogen bonds formed by this kind of interaction. The hydrogen bonding potential gives rise to some very unusual properties relative to other kinds of liquids. It's got a very high boiling point, a very high surface tension, a very high dielectric constant, as we saw in the first video, that it's because of the polarity of the protein, it's very easy for it to rearrange and respond to charges in solution. And it also expands upon freezing, which is quite unusual, partly because of this formation of these hydrogen bonded networks. Now, the structure of liquids is challenging to characterize, and it's challenging for water in particular. And the way this is normally done is by X-ray scattering in solution, and that gives the average distances between oxygens. And that's informative in thinking about what liquid water looks like on average. This is what's called a radial distribution function that can be derived from X-ray scattering. And it's basically a probability of finding a given distance at the probability of finding an oxygen atom at a given distance from another one. So you see that it's very strongly peaked around 3, a little less than 3 angstroms. It's another peak at about 4.5, and then it kind of tails off as the order from the reference molecule gets lessens. And so the kind of picture you get is that hydrogen bonded waters, their oxygen distances are about 2.8 angstroms. There's then sort of the next shell, the second shell water on average is about 4.5 angstrom oxygen to oxygen distance. And it's thought that water molecules assemble in these small networks of hydrogen bonds, often with fewer than 4 hydrogen bonds, unlike in the solid state. And it's thought that that's balance represents a balance between the minimizing the internal energy, the potential energy due to the hydrogen bonding and so forth, and maximizing entropy. Obviously, if water molecules are free to move around, they can sample more microstates, and that gives rise to higher entropy. So there's a balance there, and the idea then is that you have sort of a short-range order of waters in solution. Now, water is a very poor solvent for nonpolar molecules, and this is a table from a physical chemistry book where taking a nonpolar molecule, CH4, in solvents of different polarities, benzene being extremely nonpolar, and then ether, carbon tetrachloride, and transferring it into water. And what you see is that there is a very unfavorable entropy associated with moving a nonpolar solvent into water. Remember, delta G is delta H minus T delta S, so a negative entropy will give rise to a positive change in delta G, unfavorable. Likewise, when we look at the delta H, what we actually see is that delta H is negative, and this is in calories, not kcal per mole. What you'll see is that, in fact, it's slightly favorable enthalpically, so which may be a little bit non-intuitive. So the enthalpy of the interaction is actually slightly favorable, but it's the entropy that's not favorable at room temperature. Now, you can do similar kinds of partition experiments. This is where you take a amino acid or a side chain analog and look at it in water and then measure its concentration in water versus in the vapor above the water. Okay, so it's a different kind of partitioning experiment, but same idea. You see that nonpolar groups nonpolar amino acids, like amino acids with nonpolar side chains, R groups, like leucine and the aliphatics, really don't like to be in water. Phenylalanine, cysteine, methionine, slightly less unfavorable to put them in water. Those with hydroxyls and some polar groups start to become favorable, and more so. Okay, and arginine is the most soluble. Okay, so let's think about what it means to take a molecule and transfer it to water, into liquid. Okay, so take some amino acid. Well, what does it actually take to do that? The first thing you have to do, so here's liquid water, and they're again these clusters of locally hydrogen bonded structures at some density, some motion allowed, it's thermal motion is allowed. You need to first create a cavity in the water. You might have to make a hole in the water to fit another molecule in. Okay. Now to do that, you have to break hydrogen bonds, and in fact, one of the things that has to happen is that because of the hydrogen bonding, as I mentioned, there's very high surface tension, and you have to overcome that. Okay, so you have to make a cavity. And then you're going to throw in, let's say, a molecule of benzene. You're going to put a molecule of benzene into this. You introduce that molecule, and then the solvent itself, the water, is going to rearrange to maximize interactions. It's going to want to minimize its potential energy, so it's going to want to make van der Waals interactions with that benzene. It's going to try to form hydrogen bonds with itself. There'll be some interactions in the case of benzene of the protons of the water with the pi cloud and so forth. Okay, the kinds of interactions we talked about in the first video. So those kinds of interactions will actually be favorable slightly, and that's why you see a slightly favorable enthalpy. Okay, but think about this process. We had to open up a cavity and then rearrange things. So to displace these water molecules to make this cavity, okay, you have to order them to some degree around this nonpolar group, because the number of energetically favorable interactions is going to be more restricted. In general, for a really nonpolar group, that you're not going to really form hydrogen bonds. It's the hydrogen bonds, in contrast to hydrogen bonding to other water molecules. And it's ultimately just more restricted. Okay, the space is restricted and so forth. It's also found experimentally in solutions when you measure the partial specific volume of a solute that's in water versus a nonpolar liquid. It's actually smaller, so it tells you that the solution's more tightly packed. So again, the water molecules are more restricted. So these factors, you have a restriction, you have fewer choices, as it were, of being able to hydrogen bond, because it can't hydrogen bond to the solute, but they can't hydrogen bond to each other, but now you've lost some of the other water molecules that would have been here to hydrogen bond with. So all these factors are restricting the sort of accessible states, and therefore giving you a lower entropy. It's actually giving you an unfavorable entropy in terms of doing this process of opening up this cavity and then rearranging around the solute. Now, it turns out experimentally, if you take a solution, let's say of benzene and water, and you heat it up, it breaks up these interactions because things can move around more, okay? And it's kind of like the transition of ice to liquid. The so-called phase, about phase transitions where you melt ice, you have to put a lot of heat in right at about 0 degrees Celsius to melt ice, because that heat goes into breaking all these other interactions. Okay, and so these have very large heat capacities, these solutions. So that's a hint that, again, there is more water in these solutions than there are in liquid water. Now it turns out that if you plot the heat capacity of these solutions of amino acids, and we know their structure, so we can compute their surface areas, which we talked about in class, then there's a pretty strong correlation between the nonpolar surface area of the amino acid and the heat capacity. Again, consistent with this idea that the more nonpolar the amino acid is, the more you're forcing these rearrangements in the solution and giving rise to this larger, you're forcing these local structures of hydrogen bonded waters to each other and so forth, and therefore it is you have to add more heat to break them up. Now, if you look at accessible surface area of the amino acids and you plot that area versus the free energy of transfer, so you can again just do this transfer experiment and measure the, as we saw a couple of slides ago, measure the delta G of the transfer from nonpolar to polar solvents. There's also a correlation with this accessible surface area. Okay, and that function will depend on the solvent from which you transferred it. Okay, for example, in the plot with the x's here along this dashed line, that was from an ethanol dioxane mix into water. This is a more nonpolar solvent, cyclohexane. Okay, but the idea is that there's this very strong correlation of the nonpolarity of the amino acid side chain and the free energy of transfer. Okay. Now, in fact, because we can calculate these accessible surface areas in the context of a whole protein, this relationship is actually used to estimate the free energy contribution of burying a given amino acid in the interior of a protein or in a protein ligand interface. And some of the modeling programs you may come across actually use that relationship to try to estimate delta Gs. You can appreciate that this is fraught with a lot of problems because these are not particularly linear relationships, and it depends on your reference solvent. So there are a lot of issues with this, but the qualitative idea is very strong that you have it is less favorable to have a nonpolar side chain in aqueous medium versus the inside of a protein. Okay, so now let's imagine we talked about transferring a benzene molecule into a solution of water. How about putting in a second benzene? Okay, this would be the equivalent of making kind of a nonpolar core in the middle of a protein. You know, we know we've already seen we have nonpolar side chains packing against one another, forming nice van der Waals interactions. Well, think about that. We could put a second molecule in here, and we'd have to do that same cavitation, open up a cavity here, rearrange the water, and so forth. It turns out to be more favorable, takes less energy to put them basically next to each other because fewer water molecules have to rearrange. You also have favorable van der Waals interactions between the molecules here. And so it is more favorable to bury these nonpolar groups together away from the solvent rather than having them individually surrounded by water. And that's really the analog of having a nonpolar core in the interior of a protein. Okay, so again, you have favorable interactions here. They're certainly going to be stronger than benzene water interactions, and it's less work than making a second cavity. Okay, so all of this comes together to describe what's called the hydrophobic effect, and it's the idea that nonpolar portions of molecules want to be away from the bulk solvent. Okay, so these nonpolar groups interact with water. They do interact with water, and it's favorable, very slightly, because there still are van der Waals interactions and a certain amount of polar interactions depending on the group. So there's no repulsion. So in a way, hydrophobic is a very bad term because it's not repulsion from water. Okay, it's just that it's more favorable for water to interact with itself than with the hydrocarbon or nonpolar group. It's also more favorable for the nonpolar groups to interact with each other rather than with water. And you have to create a cavity in water to accommodate these hydrocarbons, and the displaced water molecules hydrogen bond to each other. That makes them more ordered. It's not quite as liquid anymore around the nonpolar group. And again, the idea is that the clustering of hydrophobic groups is thought to minimize the free energy required to form the cavity. It takes less work to cluster them together than to make separate cavities. There's no repulsion, despite this term, again, emphasize it. And the key idea here is that it's the relative preferences of having that group in aqueous solvent versus buried away from it that matter. It's a free energy term, okay? So there's no such thing. This is often very sloppily done in the literature. You'll see people talking about hydrophobic interactions. It's very easy to slip into that terminology, a hydrophobic bond even. But it's important to remember these are not bonds or interactions in the sense of what we saw in the first video. They're not interactions that are due to electrostatic forces like van der Waals or hydrogen bonds or electric forces like van der Waals and so forth. It's an effect due to free energy differences, not internal energy. Okay, so it's very different. So it's called a force sometimes or an interaction, but it's very important. It's a very important distinction. It's a free energy difference that's driving this effect, not internal energy. So you've all learned, we've discussed a little bit in class, that a folded protein it's a hydrophobic, its nonpolar side chains tend to be buried. We know they tend to be on the interior. And the thermodynamics of protein unfolding have features in common with the hydrophobic effect that I've been going through in these model systems. Okay? There's a very large change. If you unfold a protein, there's a very large change in heat capacity. The difference in heat capacity of a folded and an unfolded protein turns out to be proportional to the nonpolar surface area buried. I didn't really talk about this, but there's a very strong temperature dependence of enthalpy and entropy in this hydrophobic effect. So it's thought that really the hydrophobic effect is really the driving force for stabilizing proteins. It's why you have nonpolar groups on the inside. Now, it's a lot more complicated, though, than just a simple liquid, like benzene being put into water. Okay? We know that there are additional enthalpic factors that stabilize the folded state. We saw that the secondary structure elements form because you have favorable hydrogen bonds. You have hydrogen bonds forming between elements of secondary structure, like in helices and beta sheets, that are buried. Okay, they're actually in a lower dielectric environment, so they're probably even enthalpically stronger. There are also entropic factors that stabilize the unfolded state. If it's unfolded, then the polypeptide backbone and the side chains are more free to rotate and sample different configurations. So there's a favorable configurational entropy actually associated with the unfolded state. In fact, there are, in the last decade or so, or 15 years, it's been recognized that there are proteins that are intrinsically unstructured that by themselves have no regular structure whatsoever, and they're actually quite flexible and dynamic in solution, and they adopt structures when they bind to another protein. And if you look at the thermodynamics of those interactions, the entropy of the binding interaction is actually very unfavorable because you're losing all that configurational entropy. So these factors are actually essentially opposing the idea that the hydrophobic effect is what is really is the only is a stabilizing factor. So yes, it stabilizes it, but there are these additional factor of the favorable enthalpic factors that stabilize that state. And on the other hand, there are aspects of the entropy, particularly the configurational entropy, that actually would go in the other direction. That would stabilize the unfolded state. So it's a much more subtle kind of problem